Okay, so good evening, everybody, and welcome back to the third lecture of the General Material Chemistry module that we were doing for last two lectures. So, what we did in the first part of the lecture was the basic concepts of solid state chemistry as well as different basic crystal structure that we know of in solid state chemistry based on both cubic close packing and the hexagonal close packing. And then in the last class, I also introduced a little bit of what are the factors that influence crystal structure, or in other words, what controls that a particular compound will adopt a particular crystal structure. Of course, there are variety and various reasons behind this particular thing as to a compound will adopt which particular crystal structure. But there are certain general factors which we can rely on when we talk of before invoking the more complex factors about which I discussed a little bit in the previous class. First of all, as we discussed, it is the formula of the compound. Of course, the ratio of your cation and anion will also decide what kind of crystal structure will it adopt. Second, the size, absolute size of atoms and ions. Third, the relative sizes of atoms and ions and cations. And fourth is also the bonding. So one general thing that we can rely on is that if your formula of the compound is AXBY, where X and Y are the stoichiometries of your cation and anion in a formula, then the coordination number of A and B will be in the ratio of Y is to X. Okay. So provided, of course, the condition here is that your A is bonded to B and B is bonded to A. So no direct AA or BB contact occur. That is the condition for this particular generalized guideline to be valid. For example, if I have NaCl, we talked about the rock salt structure. So the coordination number of Na and Cl will be in the ratio 1:1. That is, they'll be equal. And we know that in rock salt structure, the nearest anion members of the cation are 6 and nearest cation members of the anion are also 6. So they are in 1:1. Similarly, calcium fluoride, the fluoride structure, okay, where calcium ion occupies the corner and the octahedral hole, which is your edge centers and body center. So we know, and the fluoride are occupying all the 8 octants, that is all 8 tetrahedral hole. Now the fact that it occupies tetrahedral hole, the coordination number of the fluorine or fluoride ion is 4 and the coordination number of calcium is 8. So in CaF2, the ratio of the coordination number is 2:1, 2 for calcium and 1 for fluorine, which we just talked about. Calcium has the coordination number of 8 and fluoride ion has the coordination number of 4. All right. You can, of course, try this for other compounds and you'll find this valid. Now, suppose the formula of the compound is a little bit complex, AX, BY, CZ, and let us assume that C is your anion and A and B are the cations. Okay. So, again, the same rule, average cation coordination number by anion coordination number we just talked about is in the inverse of their stoichiometry. So the same will be valid here, that is Z upon X plus Y. So what is the average cation coordination number? It is the number of the stoichiometry of A cation into the coordination number of A plus stoichiometry of B cation into the coordination number of B divided by their total stoichiometry. Okay. Now this, if you put it in the formula, which is on the left hand side, you'll be able to see that you get something like this. Okay. So for the complex structures, like the above generalized guideline of when A and B are in the ratio Y:X, we had this. When you have more complex formula containing multiple cation and anion, something like this can be applied, and this is most of the time valid. Okay. Nature of bonding. How does nature of bonding affect your crystal structure? Now, this depends upon the very simple concept that when you have ionic compound, the tendency of the ions will always be to have more and more oppositely charged ions around it. Okay. Now, that more and more has to have a limit, right? That is and I suppose I'm talking of cation, it will tend to have more and more anions around it, so that shows that it will have as high the coordination number as possible. But at some time, the anions that are surrounding the cation will experience the repulsion of the electron cloud. Okay, so that means they will be an optimum distance from each other. So if you look at both of these things, what it implies is that ionic solids will tend to have coordination number as high as possible and the symmetrical structure, which is actually, so this optimized thing is maintained by the fact as much number of anions surrounding cation, and also they should be at an optimum distance from each other. This results in ionic solids to have symmetrical structure with coordination number as high as possible. What does it do? It maximizes the electrostatic force of attraction. Whereas in covalent solids, the bonds are more directional and atoms, they generally have their preferred coordination. So the coordination numbers are relatively small as compared to ionic solid. Example, if you want to see what, just to exemplify the two things that we just mentioned, let us look at this series: barium oxide, strontium oxide, mercuric oxide. Now, barium oxide and strontium oxides are ionic. They adopt the rock salt structure. Coordination number is 6:6. Now, based on the size consideration, even your mercuric oxide should have been rock salt too. But it occurs as linear OHGO segments in its crystal structure. And that is only because this particular ion, this particular species, it tends to have more covalency in its bond with oxide as compared to barium and strontium. Okay, so this is what we call as the covalency effect. Let us take another example. If I talk about the aluminium compounds of the halogens, AlF3, AlCl3, AlBr3, and AlI3. Now you know that as we go down the group, the covalent character will increase along this series. Okay. The result is very much obvious in their melting point and structure. AlF3 adopts a ReO3 type structure. We'll talk about this structure later in the class. Okay. And because it is a more crystalline solid, it has high melting point. AlCl3, which is a little less ionic as compared to AlF3, forms layered structure. That is, it has more or less ionic kind of character within the layers, and then the layers are held together by relatively weaker bonds. So part ionic, part covalent, it has a CdCl2 type of structure. AlBr3 and AlI3, on the other hand, they show more molecular structure, wherein the predominant unit that you can see is Al2X6 unit, or the Al2, let's say Al2Br6 or Al2I6 unit. These compounds also you can regard as HCP of Br and aluminium. Let's say I'm talking of AlBr3. You can talk of it as HCP of Br, and Al occupies 1/6 of the tetrahedral whole. But in this case, each bromine will belong only to one molecule. So it's not like your ionic solid where each anion is equally bonded to all the cations surrounding it. Okay, so it's more of a molecular structure kind of thing. Effect of size. Okay, so as I said that we just talked about that in case of ionic solids, what happens is ions will tend to have as many number of oppositely charged and ions around them. For cations, it is anions. For anions, it is cations. Okay. Why? Because it maximizes the attraction. But then like charges also tend to be as far apart as possible. So as we discussed, the point A and point B imply that you will get highly symmetrical structure with as high the coordination number as possible. Now, what is that high is the real high actually? What number could it adopt? That depends upon the relative size of your cation and anion. The bigger the cation, more is the number of anion it can accommodate around it. The smaller it is, lesser is the number of anions that it can accommodate around it. So higher is the ratio, higher is the coordination number. In case of covalent solid, covalent radii do not show a large spread because the covalent bond involves overlapping of the electron cloud. So the radii will not really differ a lot, and hence we do not talk about here the coordination number is controlled mostly by the valency and the bonding requirement. Okay, so fine. So coordination number, some point that I just said, coordination number is determined largely by electrostatic interaction, whether attraction or repulsion that kind of optimizes the number of surrounding ion. Cations tend to be surrounded by as many anions as possible and vice versa. Of course, the same thing apparently it has been repeated. And why what happens is this optimum electrostatic interaction maximizes the lattice energies. Radius ratio rules, very famous radius ratio rule, all of us study it, not just in solid state chemistry, but also in general inorganic chemistry. As the size of cation increases, it can pack more and more of anions around it, kind of a very general understanding thing. The only guideline is when you are talking about surrounding the cation, okay, there has to be an upper limit up to how many anions can go around it and what will be the minimum limit, okay. So the lower limit is set by, suppose you have a cation and you start placing anion around it, okay. So you can place as many anion as long as they are the cation is touching the anion. Okay, that sets the lower limit. Because if the cation becomes smaller and it is not touching the surrounding anion, then it is a kind of an unstable arrangement. So what I'm trying to say here is that the cations must not rattle within the hole. Okay, the surrounding anions may or may not touch each other. If they touch each other, fine. If they do not, that is fine. But the cation that is sitting in the center, it should either fit in that hole, like it's touching all the anions, or it is slightly bigger than the hole so that anions are not able to touch each other, the surrounding anions. But it should not happen that the cation is rattling within the hole. That kind of arrangement is energetically unstable. Okay. So with these guidelines in mind, we can work out the minimum radius ratio needed for a particular coordination number. Okay. So radius ratio generally, because the interstices is small, so we define radius ratio as R small by R large, and most of the time, you know that cations are smaller. So that is why it is defined as R cation by R anion. So whatever I just talked about in the previous slide is pictorially shown here. This arrangement allowed R cation. Here your cation is touching all the anions and anions are also touching each other. This arrangement allowed because the cation is touching the anions. Fine, anions are not touching each other, no problem. That's a stable energetic arrangement. This arrangement is not allowed. So why? Because the rattling of the cation makes this arrangement highly energetically unfavorable scenario. Okay. So what are the different ideal radius ratio for different coordination number? We have read about this thing. So what happens is, why we are talking of radius ratio here, remember we started with the close packing. We talked about cubic close packing, hexagonal close packing. And if you're able to recall, because you're not sitting in front of me, so I can't really ask you. But if you recall that in CCP and HCP, We were talking about the spare, equal sized pairs packed in a close pack arrangement. And if you remember, there the coordination number was 12. So when this radius, there was no point of radius ratio because you had similar kind of spheres being packed. So there the coordination number was 12. But if you know that now we are talking of cation and anion, which are two dissimilarly sized species. So when the radius ratio starts decreasing, you start getting that coordination number 12 reduces to 8 and you get cubic. And those, because when your ion is closer to 1, when your cation is closer to 1, the 8 anions will be far apart from each other. They will be touching the cation, but they'll be far apart from each other. That arrangement is stable, and it would be stable till your radius ratio becomes 0.732. Then what happens is now your cation has become little smaller to fit in 8 anions around it. And now for it, it becomes more wiser energetically to take lesser number of anions around it. And the coordination number reduces from 8 to 6. So we have an octahedral coordination. And mind you, these are all the theoretical values. These boundaries that we set are not the fixed boundaries due to many reasons, which also we will talk about a little later. So this situation of a cation being able to accommodate 6 anions around it continues till this particular value, below which your cation becomes smaller to accommodate 6 species around it, and it prefers getting lesser number of anions. We move to tetrahedral regime, which persists till a radius of cation to anion ratio of 0.225, and beyond that it is able to accommodate only 3 anions. So this is how the radius ratio has been defined. And if you note that the coordination number 5 is absent, coordination number 7 is also absent. Okay, why it is absent? Because in close packed structure, coordination number 5 is not possible keeping all your cation and anion bond length constant. That means, and when I say that, I don't say that you will not find coordination number 5 and 7 in your structures. They will be present, but then those structures will be distorted structures. So if you want the symmetrical ideal structure, what happens is in 2 dimensions, if you try to make penta, let's say polygons, 5-sided polygon, and you try to fit in 3-dimensional, it does not fill in the space. That is why for symmetrical undistorted structure, it is not possible. But of course, these occur, and when they occur, we get distorted structures. Okay, so this is what I was talking about. So this is possible, it happens. Okay, but then you have this empty space. So making the entire space filled with the 5-fold coordination is not possible. And hence, when we talk about ideal radius ratios, we do not talk about the coordination number 5. So this is just an example of some compounds, their radius ratio of cation and anion. And then this is the calculated radius ratio. This is the predicted coordination number. And this is the observed coordination number. Okay. So for some of you, you will see that there are two radius ratios being described. Now, why is it so? We'll talk about it now. What are the limitations and what happens when the radius ratio are borderline? What I mean to say by borderline is, uh, suppose I'm lying right here. Suppose I'm lying right here. Now, where does my structure prefer to go? To 8 or to 6? To 6 or to 4? That is called the borderline radius ratio. So limitations, first of all, is we have to understand that this applies only to the ionic solid. Why? Because we are talking about the radii. Okay. And when we talk about the covalent solid, there is an appreciable electronic cloud overlap, and the concept of radius does not really hold good. And normally, ionic radii, how are the ionic radii determined? It first we determine the anionic distance using the techniques such as electron diffraction and all that. And then we divide it between the two ions, and this is how the ionic radii are determined. Okay. Now that interatomic distance, if you can understand and if you can visualize, will depend upon what actually is the coordination number. What I want to say is, if your M is surrounded by 6 species in an octahedral arrangement, the MO distance will be larger than when your M is surrounded by 4 species. Okay? And it will be larger than when your M is surrounded by 3 species. So actually, the ionic radii also themselves, they vary depending upon the source. Okay, so whatever we have calculated theoretically might not match. So radius ratios are just the broad guidelines. For example, I've taken the radius of oxide ion from two different sources, and I get these values. Now, if I want to calculate the radius ratio of rubidium iodide, it has 0.69 when oxide ion is taken as this, 1.40, and 0.80 when oxide ion is taken as 1.26 angstrom. What this implies is, now in this case, it will have the cubic coordination number, and in this case, it will have the octahedral coordination. So what if I go by these experimentally determined two different values, by my theoretically determined guidelines, I'm predicting different coordination number. Okay, so that's some aberrations that you are expected to come across, and that is how the guidelines work. They are not rigid, they are not strict, but they guide you towards having a better understanding and making some useful, meaningful interpretations. Also, ionic radii, this I just mentioned, I've already discussed that ionic radii are themselves a function of coordination number and the nature of bonding. Okay, so these are the things that kind of puts in a fraction of the uncertainty in your predictions if you want to go strictly by the radius ratio guideline. Also, what happens when your compounds have the borderline radius ratio? Two things can happen. Such compounds have the tendency to show polymorphism. What is polymorphism? A compound which can exist in two different crystal structure is known, is said to exhibit polymorphism, and these two crystal structure that the same molecular formula is exhibiting are called polymorphs. That is, for example, if I say that zirconium oxide at room temperature is monoclinic, you heat it to 1200, it is tetragonal, and you heat it to 2400, it is cubic, then, and it is same ZrO2. The molecular formula has not changed. Okay, so the monoclinic, tetragonal, and cubic, these are called the polymorphs of ZrO2, and ZrO2 is said to exhibit polymorphism. So when you have the cation and anion whose radius ratio are borderline, okay, then they have the tendency to show the polymorphism. For example, germanium oxide has both silica-like structure where the coordination number is 4. Each silicon is surrounded by 4 oxygen. It also exhibits rutile structure where titanium occupies the octahedral site with coordination number 6. Okay. Or sometime you you observe distorted polyhedra. For example, V5 has a ratio for coordination number 4, and it exhibits these two kind of radius ratio. Now, one predicts tetrahedral, one predicts closer to octahedral. So what will you do? What happens is, as a consequence, one particular polymorph of V2O5 has neither 4 nor 6. It shows a square pyramidal coordination, which is nothing but a distorted octahedra wherein your one octahedral bond has really elongated much more and is now unequal to the other 5. So square pyramidal means you have 4 in the planar base and 1 on the top or bottom, whatever you want to choose. Okay. Similarly, ZrO2. The radius ratio for ZrO2 is 0.68, which is very close to that of between 7 and 8. So what happens is, this predicts the coordination number of 6, but it is closer to the borderline for the 8. So it adopts the room temperature polymorph of ZrO2 is monoclinic, where Zr is surrounded by 7-oxy. And of course, the symmetry is reduced. It has now become monoclinic. Only if you heat it, it becomes tetragonal and cubic, where the coordination number now goes to 8. Okay. Now that's very interesting. When you know the expansion occurs. When the expansion occurs, the interatomic distance they increase. So the ionic radii, calculated ionic radii increases. Your ion is now able to accommodate more ions. And as soon as it's comfortable with more anions, it number of nearest neighbor anion increases to 8 and it changes to tetragon. Okay. So these are basically how to calculate cationic, the radius ratio for various coordination number. I'll discuss for probably one or two and then you will have the PPT. So it should not be a problem. So these are the simple geometrical concepts that we apply here. For example, in this particular structure, the cation is sitting at the triangular hole in the center. Okay. So, of course, it is not very visible here, but the point in the center of the cation is marked as E. So, this line is BD. Okay. So, now what is BD? BD is radius of anion. The anions are these three bigger ABCs. Okay. BD is the radius of anion plus the radius of cation. Okay. And BE, this is the radius of anion. Okay, so now I have this right angle triangle. This is B, this is D, and this is E. Okay, so I can use my this square is equal to this square plus this square, and what I get is okay. So, and this angle, of course, is 30 degree because this entire angle is 60 degree and this is bisecting. So this angle is 30 degree. So cos of 30 will be equal to B by BD. Okay. So by trigonometry, you do this. Now, what is your BD? BD, we say it is R plus R minus and BE is R minus. So R plus R minus is R minus by cos 30. Okay. You keep putting on the values. You finally reach this, and so R plus by R minus, or till whatever we have been defining it as RC by RA, this is equal to 0.15. So this is the limiting number for the trigonal coordination. When your cation is surrounded by three anions, it is touching them and the anions are also touching each other. The minimum value that should be there for the three coordination of cation surrounded by anions. All right. For coordination number 4, again we have to apply the similar concept, but here in this case, this angle is the tetrahedral angle, which we know is 109.5 or 109 degree 28 minutes to be precise. Angle ABD would be half of this, and in this angle, A, B, D, where your B is actually the cation that is sitting in the tetrahedral hole. AB is R plus R minus. Okay. And AD is R minus. Okay. So now you can apply this. Sin ABD would be AD by AB. Replace it with put it in terms of the radius of cation and anion, and then do the simple mathematical operation of taking reciprocal and all, and rearrangement, you will get the limiting radius ratio required for the tetrahedral coordination. That is minimum ratio of the cationic to anionic radii, which should be able to help you to get a tetrahedral coordination. Similarly, now I will not describe about how to calculate R plus by R minus for coordination number 6. In this, you can consider a square, and now the angle is 90 degree and 45 degree. and we'll do the similar mathematical operations. Okay, now we'll just talk about the concept that is called lattice energy. So what is a lattice energy? If I give you the theoretical definition of it, it's nothing but the energy that is required to sublime the crystal into gaseous ions and calculated in per mole. You have a solid crystal, the energy that would be required to not just ionize it, break it, but rather converting it into gaseous ions per mole is called the lattice energy. Okay. So this, or in other words, it is the net potential energy of the arrangement of the charges that are forming the crystal structures. Nothing but potential energy, because I'm not talking of any moving things here. Okay. So what will it depend upon? If I asked you, and if you've not even read about lattice energy, but you know that crystal structures are there, they are held together by, ionic, the electrostatic attraction and all that. And also lattice energy is something that is holding the ions together. So it will depend upon crystal structure. That is why different species have got different lattice energy and consequently different melting point. Charges on the ion, because more higher are the charges, more will be the attraction. Internuclear separation, the farther they are, lesser would be the attraction. And that will affect the energy that is trying to hold them together. Okay. So how can we determine it? I'll make it very simple for you. So what we do is basically in principle, if you think what is lattice energy, it's a in previous slide we said it is a net potential energy of the arrangement of the charges that form the crystal structure. So what is it? Basically, it is a summation of nothing but the summation of all the attractive and the repulsive forces. Okay, and we also know from our understanding that if we have a pair of gaseous ions, the potential energy, what will be the potential energy? We do, if you remember the physics, Q1, Q2 by R, okay? And it's 1 by 4 pi epsilon naught, Q1, Q2 by R. This is the formula for the potential energy, if you remember. And my charges here are Z plus E minus and Z minus E minus, right? These are the charges on the ion, and this is, of course, the electronic charge. So this is your potential energy for any pair of positive ion. This will be negative if I'm talking of attraction. This will be positive if I'm talking of repulsion. So this is what we take care. Now what I can do, I have to calculate the total potential energy. So what I'll do is, I will see for a reference ion, how many repulsions and attractions are happening. So what is the potential energy arising from them? And then you scale up to 1 mole of the ion pair, okay? And this equals the lattice energy of the crystal. So let us just see in another slide, how do we go about it? Take an example of NaCl, the rock salt structure. Okay, now here I want you to take a minute and think about your NaCl unit cell. So let's say I'm talking about Cl forming the FCC lattice. In this case, if your Cl is forming FCC lattice, where do I have Cl? I have Cl on the corners, I have Cl on the face center. And sodium is occupying octahedral hole. Sodium is on the body center and the edge center. Okay. I hope you've been now able to recall the NaCl unit cell. So now I have to decide, look into what are the attractions and repulsion happening for my one reference ion. Let me consider the Na that is sitting at the body center. Okay. Now this Na that is sitting at the body center, what are its closest chloride ion? Closest chloride ion are the 6 chlorides sitting at the face center. And let me assume that distance is RO. Let me fix that. Okay. 6 Cl at the face center are the next nearest neighbor of the Na plus at body center. And this is the attractive energy. So the sign would be negative because it will stabilize. Now I will talk about the like ions. How many NAs are surrounding this Na? So if you are able to recall, there are 12 Na on the edge center. So it has the nearest Na ion to my Na at the body center are 12 Na at the edge center. And they are at the distance of, now difference, if you see, if you are able to see, suppose this is my Na and I'm talking about this Na, okay? And if I join this line, this is nothing but your phase diagonal, okay? And your phase diagonal is root 2a, right? So this is and A and I, because I defined R naught as a distance between two ions, so this is actually A by R naught is A by 2. So the distance between this Na and this Na is half of the phase diagonal, right? And A by 2 is my R naught. So it is root 2 R naught. Now, the next nearest chloride ion, we talked about 6 chloride ion, which are the nearest one at the phase center. Then we had 12 Na plus, which had repulsive interaction. Now, next attractive interaction are with the 8 chloride, which are sitting at the corner of the cube. And they are at the distance of root 3 R naught. Okay, and so on. So I can actually work out as many I can, but it will obviously, this series will convert somewhere. So what I do is, I have, if I try to, suppose I try to calculate, as my reference ion is this one at the center, and I try to calculate what will be the attractive energy with this Cl. So I know it will be 6 Z plus Z minus upon 4 pi epsilon naught R naught and E square, right? And I make it negative. For this, it will be 12 positive 12 Z plus Z minus E square 4 pi epsilon naught and now root 2 R naught. Okay, and they are now 12 in number. So that also I have to determine. So now if you keep on doing it for all of these interactions and so on, I take this factor as common. What I will be left with, I also take the minus sign common for my ease. Minus Z plus Z minus, this factor comes outside. And what you are left with is a number, 6. Number of ion by this particular factor, 12 by root 2. Then 8 by root 3. Then 6 by root 4 and so on. Okay. This series will ultimately converge to a value, and this entire number that you will get in the bracket is called M, or the Madelung constant. All right. Okay. Now, because how have we reached this value? We have reached this value by assuming a particular structure, rock salt structure, wherein I had Na at the center. Then I looked into what are the next nearest chloride. Then I looked into what are the next nearest neighbor. Those were sodium ions. Then I looked into what were the third nearest neighbor. Those were chloride ion. That means Madelung constant depends on the crystal structure. That means if I am talking of the compounds which have got similar structure, they will have same Madelung constant. All right. For example, NaCl, KCl, or MgO, all of these, they crystallize in rock salt structure and they will have same Madelung constant. That is why it is called a constant, because it depends on the crystal structure. Okay. Now for 1 mole of ion pair, now this huge term I have replaced by M. Okay. And now I calculate for 1 mole of ion pair, I multiplied it by Avogadro's number. And for an NaCl type of lattice, this is a potential energy I will get. Okay. Now there is another force acting there. What is that? When your ions are coming closer together, whether they are positive or negative, their electron clouds will come near to each other, and that will repel. This is given by this expression. N is your Avogadro's number. B is bond exponent with the value 5 to 10. And sorry, B is a constant and N is the bond exponent. Okay. This also you add to this particular term. And this is what you will end up with. Okay. This is the expression. but I have to find something which is tangible and meaningful. So, because we know that the potential energy curve has a minima, so what will happen is at minimum du by dr, the slope would be 0, right? So I differentiate this expression. I will not go into the detail. Once we differentiate and solve for b, you will get a term like this. Okay. I'm just trying to reach at a point where you do not need all these derivations. This is just for your understanding. Now this b, you put it in this equation. Okay. And you will end up with this. Now you look at it. Okay. And see what all are constant and what exactly your lattice energy will depend upon. Your lattice energy will depend upon M, okay? That is the crystal structure. It will depend upon Z plus and Z minus, that is the charge of the ions. E is constant, it is the electronic charge. 4 is constant, pi is constant, epsilon naught is constant. It will depend upon R naught, and N is also Born exponent, it is constant. Okay. So U depends upon M. Of course, N is the Avogadro number or the number of species that you're talking about. Let's keep it as constant. R, the distance between the ions, Z plus and Z minus. But now suppose I fix the ionic structure also, okay? Then it will not even depend upon M. It will depend upon R, Z plus, Z minus. And because the charges, they appear as the multiplication. In multiplication together, the effect of charges are most important because they appear as a product. Now let us take what are the implications of it. If I have the same crystal structure, NGO and NaCl, rock salt structure, then Madelung constant would be same, right? But here the product of charges is 2 and here the product of charges is 4. So the divalent ion would have lattice energy, sorry, the product is 1 and here it is 4. The lattice energy will be 4 times, roughly 4 times as compared to the structure having the monovalent ion if they are crystallizing in the same structure, which is evident here. NaCl has a lattice energy of 766 and this one has 3921. Okay. Suppose Z is same. Here I talked about monovalent and divalent. Now suppose Z is same. I talk about MgO, calcium oxide, barium oxide. All of them are 2 plus 2 minus. Then higher the Re, lesser will be the UE because your R depends upon R appears in the denominator. Also, it is quite understandable. The farther they are, the lesser would be the attraction. Now here I have not kept the lattice energy values deliberately and have kept the melting point, obviously to make you understand the correlation between lattice energy and melting point. What is the lattice energy? The energy that holds it together. And melting point is the temperature at which it, melts. The ion or the atom, they move apart. Higher is the lattice energy, difficult it is to take the ions apart. So the melting point would be higher, right? So as you see here, the melting point decreases as we go from magnesium to barium. As we go from magnesium to barium, the size increases. The size increases, the radius increases, the interatomic distance increases, the lattice energy decreases, and your melting point increases. All right. So this was about some of the factors that can affect the crystal structure. How the relative sizes of constituting ion dictate crystal structure. We talked a little about bit about that. Understanding contributions of different factors that contribute to lattice energy and how broadly we can reach the lattice energy for a particular crystal structure. Okay, so we'll take a break for 2 minutes and then we'll start a crystal structure of some of the more complex solids that you generally come across in your research work or in the literature. Okay, so we'll break for a minute here. Sunny? That's the great thing. If there is any question, you can type in the chat box. The radius ratio, Shantini, is 1. There, you are talking about, when we talk of SCP and CCP, we talk about the similar kind of atoms forming that this thing. That is why till, for every coordination number, you have the range of radius ratio. So 1 or above, it is 12. It is able to take more ions. As you go below 1, then it starts moving towards the cubic coordination number. Radius ratio is of course 1 because the closed packing is formed by similar kind of ions. In fact, the concept of radius ratio there will not arise. Okay, so we'll move on to some interesting structures. Okay, first one of them, the one that is probably one of the favorites of material scientists or solid state chemistry, and so myriad functionalities are perovskites. I'm sure most of you have heard of it. The general formula for perovskites is AbO3. Okay, so they take their name from the mineral, which is and named after the Russian mineralogist Lev Perovsky, but they were discovered by Gustav Rose in Ural Mountains of Russia. Many a times people are asked this generally. So who discovered perovskite? And there's a very general tendency to say that Lev Perovsky. I myself did it when I was asked this question for the first time. But of course, I thought because of the reason that I myself mentioned it wrong, I would want you to remember it. It is named after Perovsky, but they were discovered by the Russian mineralogist Gustav Rose. Okay, so little bit things about them. Why I start with ReO3 structure? Because AbO3 structure is based on ReO3 structure. So what is ReO3 structure is? It is basically your cubic closed packing, but now rather than a similar anion, one anion forming CCP, it is both Re and O are forming the CCP with 1/4 rhenium ion and 3/4 of oxygen. Okay, so the CCP is formed by rhenium and oxygen ion, but rhenium are in the ratio 1/4 and oxygens are in the ratio of 3/4. And this is how it looks like. These are the octahedra of ReO6 and they share corner in 3 dimension. Or in other words, it look like this. Okay. Now, how does AbO3 structure generate from this? In that cavity between each 8 polyhedra, you place a ion. Okay, so your rhenium, you had ReO3, rhenium you replace by BO3, and in the cavity, you place a cation. That is your AbO3 structure. Okay. In terms of unit cell, how, of course, why it is important is, as I said, one class of compound that shows you the spectrum of properties. You will find conductors in AbO3, you will find insulators, you will find superconductors, you will find dielectrics, ferroelectric, mixed ion conductor, lithium ion conductor, giant magnetoresistant material, and this is all because it is a very, very flexible class of material. And we'll just talk about it a little more. Okay, first let us see how to represent a typical ABO3 cell. There are two ways. Generally, it is represented by A type. Why do we call it A type? Easy to remember when I'm putting A at the body center. When I say that you have two types of unit cell, that doesn't mean you have two types of unit cell. Let's be very, very clear about it. That means there are two ways by which you can represent your unit cell. So if you are taking A at the center, then your B ions will be at the corner. Simple. Okay. And your A ions will be all at octahedral, all at the edge centers. Okay, that is one way. A at the center, B at the corner, O at the edge center. On the other hand, if you want to keep B at the center and we call it B type, what happens is now your A will take the corner. When A was at center, B at the corner. Easy to remember. B at the center, A at the corners, but now oxygens will be only at the face center. Now, the most interesting part is since they are not different, you can actually visualize B type when you look at A type. How? Concentrate at this particular B. Okay, let's say this B. All right. So, how many oxygen does it have around it? One, and then two, this, and then you have uh, okay, I'm talking about this particular this. Okay, one, two, right? Then there'll be adjacent unit cell and an oxygen would be here. Okay. Similarly, you have an oxygen here, so obviously one oxygen has to be in front. Then one oxygen here and one oxygen here. Okay. This is what you have here. B at the center and 6 oxygen as octahedra. And how many O's? You have B at the corner and A was at center. Now around this B, you have 8 cubes, 3 surrounding it in the same plane and 3 on the top. And each of those cube has got A at the center. So the B is surrounded by 8 A's and this is what you have, 8 A's. Okay. So I hope that clarifies it. Of course, you can remember the way as I said earlier, when A at the center, B at the corners, B at the center, A at the corners. But when A is at the center, oxygen are at edge centers. When B is at the center, oxygen are at face centers. But as I said, you can derive one from the other. Okay. And how do I describe it in terms of space filling polyhedra? Since we have, this is very clear from the B type, we have a BO6 octahedra, okay? And if I go on the previous slide, you can easily visualize your BO6 polyhedra are sharing corners to form three-dimensional network, okay? So in terms of B, this is how it looks like, BOB polyhedra. What about A polyhedra? Okay. Now A is surrounded by, and I'm talking of oxygen, polyhedra made by oxygen. Let me be very clear about it. Okay. Because here you have multiple ions. When I look at A, okay, I have a 12 coordinated polyhedra made by oxygen that are lying at the edge center, which is called a cuboctahedra. Okay. Now imagine you have a cube here adjacent to this particular cube that I'm talking about. A and A would be at the center of that cube. Okay. And this face will be, this particular face will belong to this cube also. So these 4 oxygens will be the part of A polyhedra here as well. So what I'm looking at, I'm looking at face sharing AO12 cuboctahedra. Okay. Face sharing AO12 cuboctahedra. So when I want to represent it in terms of B polyhedra, it is corner sharing BO6 octahedra. When I want to represent it in terms of A polyhedra, it is a face sharing AO12 cuboctahedra. Okay. Talking about the coordinates, very simple. Your B ion, I'm talking of strontium. This is strontium titanate here. So A is strontium, B is titanium. Your B ion is at the corner. Lattice coordinates are 0, 0, 0. Simple. A atom is at the body center, half, half, half. Oxygens are at the edge center, half 0, 0, 0, half 0, and 0, half 0, 0, half. 12 oxygen, each edge contributing 1 by 4, 12 into 1 by 4, 3 lattice points, and this is what you have. The formula comes out to be 1A, 1B, 3 oxygen. Okay. Now, why, as I said, it shows so many properties because effectively, if you look at the periodic table, the one that are surrounded by circle represent the A side, represent the element that can occupy A side. The one that is surrounded by, represented by this hexagon represent the element that can occupy B side. So if you look at it, virtually more than structure in some combination or the other. Okay. So when you have so many different kind of elements which can adopt this structure, obviously it will show you a variety of properties because properties will depend upon the elements. Okay. Now, I will not talk about the upper part. I've already talked about it. Well, okay, when I say that so many structures are possible, but when I talk of perovskite typically is the cubic perovskite. So, what will be the radius ratio of A and B with respect to oxygen that they can adopt a cubic AbO3 structure? Okay, so that is given by 2RB. Okay, how they have derived this. Just look at this particular cube. I will not take a lot of time, but if you try to see what is the A is the lattice parameter, okay? And this is your oxygen, and this is your B, and this is your A. What is A? A is, because here I have 2B and this is 1 oxygen, 2 RO plus RB is my A. Okay. So what is your A in terms of the radius of A cation? If you see, they are A cation and your oxygen anion are touching each other along the face diagonal. Okay. B was touching along the cube side, but it is touching along the face diagonal. Your face diagonal is root 2A, right? So 2 RO plus RA is root 2 of A. Okay, this is what has been written here. Now all of them are equated. The relation that you get is RA by RO is root 2 RA by RO. That means this relation has to be satisfied if you want a cubic AbO3. Okay, now this is when it is 1. If I take the ratio of this, I just bring it into a in the denominator. That is, I write as RA by RO upon root 2 RB by RO. I call this number as T, which is called the tolerance factor. Okay. If numerator and denominator are equal, tolerance factor is 1. You have cubic perovskite crystallizing in the form we have been discussing till now. But as I told you, now this structure has got a lot of flexibility. Okay, let me just see this way. Okay, look at this structure. Right, this is your cubic perovskite and it supports a particular radius ratio of A, which is given by that tolerance factor formula. What happens when A becomes smaller? Okay, now as I said, your cation that is lying in the interstices, it cannot become really, it cannot stop touching the anions because otherwise that situation will be unfavorable. If it was, now the speciality of this AbO3 structure is, now if this radius of the cation A becomes smaller, it can still accommodate it without losing its BO6, without losing its local coordination. And how, what will happen is, these 8 BO6 polyhedra that you look here, right now they are straight. What they will do is they will tilt inside. Okay. So that they now accommodate a smaller A. Okay. So, but what happened is now structure has gone from cubic to some other structure. Not exactly cubic, but some distorted cubic. Okay, but AbO3 still remains. So that is how this structure is flexible. So when you have, and this is what this slide is trying to tell you, when you have tolerance factor as 1, you have cubic structure. As you decrease it, decreasing the tolerance factor means you are actually decreasing the size of A or you are increasing the size of B, right? It will become orthorhombic. That is now your polyhedra tilting to fill in the space. And if you still keep on going lower, there are variety of structures possible for this nominal, wherein your composition will still remain AbO3. So you have ilmenite, you have C-type, and of course I will not talk about them here, but I'll just leave it at that, that they are very, very interesting crystallographic cases to study. And if you go beyond 1, then of course your corners sharing changes to face sharing. And then you land up into some other crystal structures. Okay. So this is how, and this tolerance factor is, this ratio is also called Goldschmidt ratio, or which was actually given by Victor Moritz Goldschmidt. Okay. So yeah. Now, depending on, based on these perovskite, we have certain layered perovskite, that is how interesting the crystal chemistry gets, because uh, keeping in mind few guidelines, there is an option to create different structures. Okay, just you have to keep in mind for few basic guidelines which should not be violated. So based on perovskite, we have 3 classes of layered perovskite. You don't really have to cram this. I'll only make you understand the basic fundamental. One is called Dion-Jacobson. Now, what is Dion-Jacobson? Nothing. Basically, you have layers of AbO3, CbO6 polyhedra with A atom, A ion in the center. Layers of AbO3, and in the middle, they will be interspersed by, this is layer 1. This is layer 2. In the middle, they'll be interspersed by a different A cation, a layer of A cation. And they call Dion-Jacobson. And what is this N? This N actually represent, now here they are showing 2 layers of BO6 joined together. N is how many layers of BO6 will join together. That characterize that particular Dion-Jacobson structure. Okay. Rudless and Popper. Here you have slabs of BO6 similar to what you had in Dion-Jacobson, but in between you have AO structure of rock salt type. So you have perovskite interspersed by rock salt structure. The difference is this A in the perovskite and the A in the rock salt are different. Okay. Aurovelius. Aurovelius, you have BO6 slabs of AbO3 interspersed by Bi2O2 fluoride type layers. Now, why are these systems we study at all? They look complicated. They are not, and they're super interesting in terms of the because you can see that they have layers in 2 dimensions. So they're very important and very interesting system for investigating the 2-dimensional physical properties. Okay, so because we cannot go into details of those, so we'll just move forward. As I said, AbO3 is a delight of material scientists. Why? Variety of tolerance factors are allowed. Of course, there will be distortion in the structure, but the formula will remain, the basic framework will remain the same. Then A and B side are insensitive to charge distribution also. So for the same AbO3, see, charge neutrality has to be maintained, right? If I say I can put any A, any B, that's not possible. Now you have 3O, that means you have -6 anion. So cation, the charge, total charge has to be +6. But there are very few structures which will allow permutation of this +6. AbO3 is one of them. You can have 1 and 5, sodium and tantalum, Na plus, Ta5 plus. You can have 2 and 4, Sr2 plus, Ti4 plus, LaMnO3, 3:3, La3 plus, Mn3 plus. So various valence combinations are possible, maintaining the charge electroneutrality. and the structure can also withstand considerable departure from ideal stoichiometry. And in fact, these non-stoichiometric configuration give you further interesting properties. For example, you have LaSrTi 2.5. I mean, AbO3 may A side pe you have put in two ions. And then oxygen also you have taken, it is oxygen deficient material. But still, the basic framework remains. The structure does not crumble. A site you can have a lot of deficiency. So if you see it is La 1 by 3 tantalum oxide, this compound exists. And if you just imagine, actually 2 by 3 of A site is lying vacant here. Still the structure remains. And you know, it's just not about it is vacant and it is forming. That vacancy will lead to many interesting properties which will have a lot of practical uses. That is how the studying the crystal structure and realizing what exactly is special in that structure that is yielding that property is important, and that is actually all the structure property correlation is about, which is probably the most researched area in science today. These are perovskite related structure. I will not go into a lot of detail. Why are these structure important? Because they are the basis of superconductor. So you basically have stacks of one unit cell of this particular structure is nothing but a stack of three perovskite type unit cell. So how they are arranged? One A type, one B type, and one A type. Okay, you stack them, and then bottom layer of this A type and top layer of this A type is removed. This B type remains intact, and you stack them one over other. Okay, you get the unit cell of K2NiO4 or La2CuO4. All right. Why they are important is because these kind of compounds are superconducting compounds. All right. Now they are tetragonal. Obviously, you can see when you stack these one over the others, your A is equal to B, but your C is now three times. So they become, they from cubic they transform to tetragonal. Okay, so one of the first oxide which was known as the high temperature superconductor. High means it you was a superconductor above liquid nitrogen temperature. That is why it is called high temperature. Otherwise, it is at around 80 K or something. It is YBO2Cu3O7 because the stoichiometry is Y1Ba2Cu3. It is also called 1,2,3 oxide. So whenever you hear of 1,2,3 oxide, it is these kind of oxide. So this was one of the very first high temperature superconductor discovered, and its unit cell is formed by stacking three A-type unit cell of the perovskite. The fact is, the bottom A type and the top A type are BaCuO3, where your A cation is Ba, B is of course Cu, and the middle one is YCuO3, where your A cation is Y and Br of course again copper. Okay, so this gives you, because it is three stacking up of three AbO3, so your oxygens have become 9. Okay, and your cations will also become, you have two cations here, 1 or 2. So when you make it three times, it will become 6, and this is what you have, Y1, Ba2, Cu3O9. But this compound as such is not a superconductor. The superconductor YBA2Cu3O7 has got two missing oxygen. And where do those oxygen go from? These two go, okay, these four go, and these two go. Okay, and how they correspond to 2, like from 9 I go to 07, because these two, these four are now they are the edge center. They are contributing half, 2 into 1 by 4 half, and 2 into 1 by 4 half, and these are also the edge center. 4 into 1 by 4, 1. So 1 half, 1.5, 1.5 plus 0.5, 2. So from 9, you subtract 2. And when you remove these 6 oxygen, rather these 8 oxygen, from YBA2Cu3O9, it becomes YBA2Cu3O7. Even this is not a superconductor unless it becomes a little oxygen deficient. That is by Ba2 Cu3O7 minus X. Okay. So for X value of 0.65 and above, this is a superconductor because there is so much restriction on this X value. And you imagine, I cannot really control oxygen because oxygen is present all over. So the environment of synthesis has to be controlled. It is difficult to synthesize. Oxygen stoichiometric control is most of the time not very easy. Redox atmosphere has to be controlled. Usually the material obtained are 6 plus X. And then what we do is we control our oxidizing and reducing atmosphere. And the maximum TC, maximum superconducting temperature has been obtained at O 9.9. Okay. So we are left with just one or two more structures. So have patience with this. Brown millerite, simple to remember. This is your perovskite. All your BO6 are linked by corner. Now out of this, every alternate layer, okay, this, then 1, 2, 3, and then 4. If I make tetrahedra, octahedra, tetrahedra, octahedra, tetrahedra. Now these are octahedra, these are tetrahedra. These are octahedra, these are tetrahedra. So what it is actually equivalent to, your AbO3 is perovskite and AbO 2.5. This is defect perovskite. But if this oxygen defect that is arising in perovskite, it orders. And orders in what form? That half of the octahedra they convert to tetrahedra to absorb that vacancy. And happening in that ordered manner, every alternate layer, you result in brown millerite. You twice this up, A2B2O5, and this is called the brown millerite structure. I'll repeat again. If from AbO3, 0.5 oxygen per unit cell is taken and it is disordered, I mean, one polyhedra will have all 6, one will have 4, one will have 5. That means it is disordered. You get defect perovskite. That is, your XRD pattern will still be like perovskite. But if that oxygen vacancy orders in such a way that your alternate layer of corner sharing octahedra become tetrahedra, you end up with brown millerite structure. Okay, and they are very, very good ionic conductors. Spinel structure, I would not spend a lot of time in. Just that a spinel unit cell is, you remember your FCC unit cell? I will not repeat it now. Stack 8 FCC unit cell, okay? Not on one top of each other like we did for perovskite, but to make a bigger dice. Your FCC unit cell is a smaller dice. Now arrange 3 dice around it and then 4 on the top of this so that you get a again big cube of 8 smaller FCC. That is the unit cell of your spinel structure. Spinel ka formula is AB2O4. Okay. So if you have FCC packing, now your oxygen are 4, your tetrahedral holes would be 8. Okay, tetrahedral holes are twice n. Octahedral holes would be 4. Okay, so now you have FCC of oxygen. Now A cation, they occupy tetrahedral hole. But if you see the stoichiometry, for every 4 oxygens, you have 1 A. So only 1/8 of the tetrahedral holes are occupied. All right. These B cation, they occupy octahedral hole. But again, since they are half the number of your oxygen, half of the octahedral holes are occupied. And that is your spinel unit cell. I'll repeat it. Spinel unit cell is made up of 8 FCC cell. Okay. Anions form the FCC lattice. A occupy 1/8 of tetrahedral. B occupy half of the octahedral. That is normal spinel. For inverse spinel, what happens is your B cation, half of the B cation, they go to the tetrahedral hole and A entirely moves to the tetrahedral. Octahedral hole. Okay, that is your inverse spinel. This only shows the occupancy of the whatever I just taught. This is how the single units, the structure of MgL2O4, which is a spinel AB2O4, looks like. So the factors that decide whether it is normal or spinel, inverse spinel is relative sizes of anion, Madelung constant, because Madelung constant has to be very favorable, and it is a factor that depends on crystal structure and also the crystal field stabilization energy. Last structure, pyrochlore. Okay. Again, like perovskite, this is one of the classes of the solid state chemistry. So I'll describe it in a very, very simple manner. This is your FCC structure. Defining it for the last time for you now, you have uh, the cations at the corner and face center, and these red balls are oxygen. They are at the 8 octants, occupying tetrahedral hole, giving you the formula AO2. Okay. Now suppose I substitute, now in AO2, what is the charge? All of you are chemists. What is the charge on the A ion? 4 plus, right? If I substitute some of the B3 plus in place of A4 plus. Now, whenever we substitute any ion by a aliovalent ion, when what is aliovalent? The charges are not similar. Okay, the charge discrepancy would be created between the negative and positive. That should not happen. Electroneutrality has to be maintained at any cost. Now, when positive charge has decreased, some of the oxygen will be removed. Okay, what happens is some of these yellow balls will be occupied by B, and some of these red balls will go away. These are oxygen. What you get is the fluoride now becomes defect fluoride. It is represented as AbO2 minus X. Now suppose these B3 ions were 50%. That is, half of the A ions have replaced them. Again, like first situation, half of the A plus are replaced by B3 plus, and accordingly, equivalent number of oxygen vacancies are gone. Okay. But those oxygen vacancies are randomly there. Like in one cube, two of the oxygens are gone. From one is gone. From another, none is gone. That is still defect fluoride. But if the situation happens, and that depends upon the relative sizes of A and B. If the relative sizes of A and B are favorable, what will happen? Every alternate A will be replaced by B. That means, and along all the three directions. If this is A, this is B. If this is A, this is B. The one at the back is B, and only the next one is A. Okay. That means your unit cell is still cubic. It has become twice. Along with that, the position from which the oxygen goes, that also becomes fixed. That means if this oxygen is going, then only this oxygen will go in all the units. Now the structure that results is called the pyrochlore structure. Pyrochlore is nothing but an ordered structure of the fluoride. So I hope this is clear. Repeating it again, if you replace 50% of A4 plus by B3 plus, and if the radius ratio allows for it, there will be an ordering of A and B cation along all the three directions, and the oxygen will get removed from a particular lattice site. Then the fluoride structure transforms to pyrochlore structure. Okay, that is what pyrochlore structure is. Again, like perovskite, very, very versatile class. You have conductors, you have catalysts. They are also used for nuclear application. They are futuristic nuclear matrices for various concepts. Optical material, thermal barrier coating, they've got very low thermal conductivity and they show magnetism. Okay. This you know, but just for the sake of completion, you know the structure of common nuclear material is fluoride. The common nuclear material that we encounter is UO2, PuO2, and thoria. And Ceria, for those of us who do not directly work with nuclear materials, Ceria is called the surrogate of these materials. So structurally, solid state wise, Ceria is similar to these compounds, except the fact it does not have radioactivity. So they all of them crystallize in fluoride structure. Then the carbide fuel, you know how important this is for us. CuC, PuC, THC, and UN, all of them, and the nitride fuel. They are 1:1 stoichiometry of cation and anion. They adopt the rock salt structure. That is one ion form FCC and the other occupies the octahedral hole. Okay. So I'll finish it here. We studied about the factors that affect crystal structure. We studied what perovskite are, perovskite base structure, Dion Jacobson, and your brown mill, and of course the other two structure that I talked about. Rudliston, Popper, and Aurovilius. Then we also talked about the brown millerite structure. We touched upon spinel, and we discussed what the pyroclore structure is. So we'll finish up here. In next class, there'll be a small section on how the structure affects the property. And this I always teach because there is no point in studying structure after structure unless I understand the importance of studying structure. As I mentioned sometime in the last half an hour, it is the structure that control the property. So if I have to design a material with better property, I have to know how structure controls my property. So I would want to dedicate at least some time to it, and then we'll move on to further topics. So I'll break here. You have 2-3 minutes to write in the doubt in the chat box, if at all, and then we'll call it a day. Thank you. The logic for radius ratio would be same because it ultimately decides how many anion can surround cations and vice versa. Basically, how many bigger ion can surround the smaller ion. I would be happy to address any more doubt that you would have. Shantini, I always prefer AR West. If you have any other book, you can go through it. But for the basics, AR West has always been my favorite. Okay, so I hope there are no more questions and we can close the lecture here. So I'll see you on Monday. Yeah, thank you.